2063, okay? So I lead the Department of Data Management, Digital Products and Technology. So what we do there is to use remote sensing data, artificial intelligence, any technology that can help to support African countries in their agricultural transformation. We have several departments, knowledge systems, policy innovation, and so on. And we see ourselves as mobilizers of expertise, and we support African countries and working closely with the African Union Commission. Okay. Now today my presentation is a chapter that we published during our annual Trend and Outlook report from the RISACS, the Regional Strategic Analysis and Knowledge Support System, and it's entitled Using Remote Sensing to Understand Methane Emissions in Africa. Now, what is interesting about this topic is that most of the time, African countries, they collect their data at the national level, and they try to have, it's not working? Not the mic, the headphones, okay. And they collected the data and by sector about methane, and then what is interesting here is we know the data gap that we have in Africa most of the time. So when they report about methane, we see some discrepancies in the data. We're not sure about if they cover a lot of stuff about it or not. Now we see an opportunity with the recently launched Sentinel-5 satellite to start having a baseline about methane emissions in Africa. So that's the purpose of this chapter. Now, my presentation is a four-fold presentation. I will start with justifying methane tracking when it comes to Africa. And because here, most of the time, you hear that Africa should focus on adaptation and not on mitigation. I'm not so sure about that when it comes to methane and other greenhouse gases. Data and methodology result from the chapter. So we did some use cases for 4 African countries, and then the perspective. I will start with one key message, which is the main, let's say, point of the chapter, just to have a baseline of methane emission. Whatever the source, we just want to know how much Africa is emitting in terms of methane, and then see where we are compared to Africa average, the global average, and then what is above average. What we realize here on your left is that there is a gap of plus almost 600 parts per billion of methane compared from the African average to the global average, right? So meaning that Africa as a continent is emitting less than the global average. It doesn't mean that for some countries it's not high, right? And then now on the left you can see for 4 countries, Mali, Namibia, Niger, and Nigeria, what's the percentage of global average methane concentration here compared to the global average. And in the middle, just to put things in context, like how methane emissions is evolving in the world, like seeing the inflection point around 2000, 2005, right? Now, for the first chapter here, the first section, justifying methane tracking. So, as I said, most climate change mitigation adaptation discussion have focused a lot about like carbon dioxide, but recently we realized that methane can be interesting. Actually, it's a low-hanging fruit and a winning strategy when it comes to reducing or mitigating greenhouse gases because of also its lifetime in the atmosphere, around 12 years here, and also, as you can see from the IPCC 2020, that the removal of 1 ton of methane corresponds to around 84 and 86 tons of CO2 removals. That's interesting, actually. Bearing in mind that CO2 will remain in the atmosphere longer, way longer than methane, actually. So it is one of the justifications why methane can be a winning strategy to reduce the global warming, as such that it is implied or a consequence from greenhouse gases concentration in the atmosphere. So second, if we look at the budget about methane, so it appears that there are a wide range of sources, but not that much of like sinks actually for methane. And most of them actually are like chemical reactions, and often they tend to also be reinforcing, meaning those same removals can also lead to re-emissions or the methane, let's say, as a byproduct of chemical reactions. And if you look at some sources, like we are, in the world, we emit between 500 and 600 teragrams of methane per year on average. But the things are between minus 460 and minus 580. Interesting. But me, when I see this, I say, okay, so us as the world, we just have to manage between 20 and 52 teragrams CH4 per year and we're done. But that will be misleading because actually we don't see the reinforcing patterns and also the impact of some erratic climate events like heavy rainfalls, or you have also flooding. In my country, in Senegal, for example, this year we have a heavy rainfall in the north, like a lot of flooding things happening in the north. So therefore there, I would expect that with an increase in temperature and having that substrate available and also the water table depth, therefore methane can happen, the methane emission or methanogenesis. And I will show a graph at the end where you can see the relationship that we are trying to derive from those three parameters. And now what we want to do here is like a, here is like a graph also that we took from one of the reports from the IPCC as well. When you look at the emissions, you have several of them, and also you have the range of emissions from hydrates, livestock, rice cultivation. For example, Senegal is a heavy rice cultivation country as well, and wetlands as well. You have the mangroves as well. So there you have actually several sources, but if you look at the things, like for example, stratospheric OH, you have tropospheric CL, and you have also the oxidation in soil. So those are chemical reactions actually. So you cannot like say on trees I can, for example, capture the methane and so on, even though it might happen, but it's not the main, let's say, mechanism that that item is doing. So the most effective ways, or one of the most effective ways, is to tackle the source right away. But in Africa, what is tough though is, and complicated is, what are those sources emitting really? Can we have a realistic measure? Because if we don't do that, we might have a biased view of what the country is really emitting. Therefore, we can open the doors for decision makers or decision making that might be misleading as well. Now, in Africa, there is a political will to combat climate change, but often they will face some hurdles on, for example, the institutional arrangement that needs to happen, the type of capacity building or human capital that you need to do that in terms of data capacity and data availability, data accessibility. So what I mean by that is you might have the data available but not accessible to you. So therefore you still have to fight and work harder to get access to the data. And that's where actually having access to remote sensing data is interesting, because it's democratized and open to everyone. Therefore it means that some assessment somehow can happen. And so here, what I also wanted to emphasize here is that the mitigation is not only a problem of industrialized countries or developed countries, it's also about those who have like a huge landscape and are also managing their lands in a way that also, emissions can happen. Now, how can we also, while we focus on adaptation heavily, we also help to mitigate on the other side when it comes to methane as well. So that's the whole purpose of this work. So basically a stock-taking exercise. Where are we in terms of methane emission in Africa? At least can we have a proxy of it, and can we compare it with the global average? Now in the methodology, here we are, I'm not going to spend too much time here, but we use the Sentinel-5 Sentinel-5 satellite from the European Space Agency, from the Sentinel family. They have 1, 2, 3, 4, all the way to 5. And this one has been built actually to be able to measure some greenhouse gases, but also short-lived pollutants in the atmosphere. So the measurement is like measuring the concentration of gases for a column dry of air, and with the sensitivity of the first layer, the troposphere, between 0 and 10 kilometers, which is the one that is the closest to our atmosphere as well. So here we really spend a lot of time trying to figure out if the data is really sensitive to the first layer of the atmosphere, therefore it can be used as a proxy for emissions. It is a weak link, but at least it helps to have an estimation. And here, I'm not going to spend too much time here also, but the way it is done also is by looking at the atmospheric abundance. So basically you have a, like, imagine you have a cube, you have gas inside, and then you send a light. And then when the light is sent, you look at what is transmitted on the other side, what is not. And from there, you'll be able to look at the abundance of the gas. And this is the principle that is also within the Sentinel-5 as a payload. And here you can see the transmittance here, the total one at the top, but underneath the first panel, you can see the one for CO2. So therefore here you can guess that this disturbance for the transmittance here is provoked by the presence of carbon dioxide. And then here you have the one for methane. So that's the way it is done. And now, and here I just explained that where the like spectral range where methane actually is absorbing that light. When you take that principle on a satellite, and then now you have a flight system where you have the flight direction, the wavelength. So basically you have the scanner, if you can put it that way, or the sensor that will scan Earth, and the data is available daily, but on a weekly average, shared on a weekly average. Now let's talk about the validation part, because it's very interesting to have the measurement, but if it doesn't match like the value that you have on Earth, it might be a bit challenging to use the data for research. Now here you see there are some colleagues that did this work. You can see there the publication. And what they did basically is they have a network of sensors for methane on the ground, and then they tried to measure, to compare the methane emissions from the satellite and from the sensor on the ground. But not only to compare, but also to calibrate what the satellite is saying as well. And then from there we can rely on the satellite, and from time to time trying to make sure that there's no divergence between the measurements and the real value on the ground. Another one also is here the comparison between here the concentration on the ground with the sensors with TCCon, and then here you have the concentration provided by Tropemy. And for like a number of 3,200 data points. One might discuss that this is not a lot of data as well for comparison, but given the sensors that are available, it seems to be like a good alignment after calibration. Now, here I just wanted to show what's the result for Africa, okay? I don't know if you are comfortable with Africa, like about which countries where, but here basically is where you have dense vegetation. That's where you have actually the highest concentration. It was a surprise to us, saying like, okay, where it is green, that's where you have a lot of methane, but is it really a surprise? Because at the end of the day, this is where you have a lot of rain, and then you have a lot of vegetation cover, and also that methanogenesis can happen easily there compared to some other dry regions, for example in the north, in the Sahara, and for example in the south. That is a surprise still, because there are some activities in particular livestock that are happening in the south, and also you have some industrial activities that are happening there. But to what extent can we say that they are correlated with what we are measuring? That's one point. Now, I'm going to go a bit deeper for the use cases, and also some analysis that we did here to compare croplands versus non-croplands. Okay? On your left, you see this is the map of Mali. Okay? And Mali, you see that Bamako is on the southwest. In the north is basically a lot of, it's like the desert. Okay? Now in the south, you see that the concentration is between 1920 and 1940. At this point, we don't know yet what is too much, what is too low, what's what. We just want to know how much. And then from there, maybe comparing with the global average, that's where we can start seeing like, okay, this is too much compared to a threshold, for example. what we did now here is, and by the way, this data is published on the chapter in the ATOR. It's shared also with country officials, and then to be able for them also to let them know, okay, we have this here. If you're interested, we can also discuss about some validation aspects. We're trying to put some sensors on the ground as well, when possible. It's not yet the case, but at least to be able to have our own validation work as well. But what is interesting here is you see the cropland moving average here in orange, and then you have the spot vegetation moving average, basically non-croplands, so something like that. It's not something like that, it's not cropland actually. And what you see the green, basically on croplands, you have a higher concentration of methane compared to the others. However, the trend is the same. Now, what are the land management practices that are happening there that can explain similar trends? Or for example, what explains that after like this point in June 5th, 2023, that the methane start increasing? Is it because we are getting into the rainy season? Yes, it is the rainy season in May, June, July, and going to the summer. And from there, you start seeing that the methane peaking. So basically, what we can say for us here is that it is correlated with the seasons in the country. Now, to what extent can we say that if you have this amount of rainfall and temperature, you will have this amount of concentration in methane? We don't know yet also. But at least we want to just to learn the dynamics of methane emissions in the country in using the croplands versus non-croplands and through time. Okay, and now this is Namibia, and then here we see there is no, at least it's pretty green. It means that actually the concentration level is low. Namibia also has a lot of desert, and the comparison between cropland versus non-croplands is quite different from what we saw in Mali. And then we see that there's an increase most of the time during like the beginning of the year here, and then there's a decrease here, even though you have the rainy season here in the middle. So this is like counterintuitive compared to what we saw in Mali. And again, without looking at this, for example, profile, we won't be able to see that there are different profiles in methane emission in countries. Now the next step would be to know what are the human actions on the ground that are really impacting this behavior, and is there any way that we can reduce, for example, if we understand what happened in this period that lead to, for example, an increase in for example methane emissions or concentrations, maybe we can find a solution to say, can we reduce it a little bit? One example in Senegal is that we realized that the rain-fed rice cultivation emits more greenhouse gases than the irrigated one. It's completely counterintuitive. And then now we are in a heavy debate with the national research centers and try to validate that. Some of them agree, some of them not, but if it's, for example, real, it means that irrigation becomes a solution. Now, what are the barriers to irrigation in Senegal, looking at the landscape and so on? That's another issue, but at least let's do irrigated rice. Maybe we can reduce our greenhouse gas, methane emissions. That becomes interesting. That's the reason why we try to do this kind of research. Another one is here, this is Niger. And again, Niger also has a big part in the Sahara, in the Sahel, so it means that it's basically wherever you see green in the Sahelian countries, it means that it's desert, right? And then now in the south, you have more agricultural landscape, and you have farmlands. You also have economic activities and industrial activities in there. Now here, similar to Mali, we see that the trend is similar. And the peak is at the end of the rainy season. So it's not in the middle of the rainy season, but at the end. Does it mean that it rained enough, there's enough water, and the temperature is high enough, therefore the methane increase? So we don't know yet that also. But we see that for Mali and Niger, the trends are the same, and usually the methane emission above croplands is higher than elsewhere. Nigeria. It's not green at all. It's maybe a small part in the north that you can see. But when I saw this, I was pretty happy, not to say that yes, we're emitting a lot, but more to say that, okay, we see changes between countries. and countries that have a different level of economic development. And that becomes interesting. Nigeria is one of the most developed countries, if we can put it that way, in West Africa, right? Compared to Mali, compared to Niger, and so on. And you can see here in the south where you have a lot of, for example, economic activities, oil and gas as well. And you have also cement industry that are very heavy in process. We see that, okay, we have there a lot of, for example, emissions. And also it's a densely populated country as well. So what's the correlation with that? Causality or correlation? We don't know yet. But it's challenging to say something right now, but it's better like to further investigate what are the aspects that are prominent when it comes to methane emissions in this country. And similar here, we have similar trends, but well, it's a moving average, so sometimes it's also, let's say, inherent to the methodology. And we see also here there is maybe a small window where actually the emissions are the same for croplands versus non-croplands. That also we don't know what it means, but at least we know that what are the levels and the dynamics of methane emissions in the country. Yes. Yeah.
A really big spike there that you pointed out. Is that attributable to anything?
This area?
Yeah.
That we don't know. The only let's say explanation we have is when we compare these results with the growing season in the agricultural sector. And actually what is interesting also is non-croplands versus croplands. What are like the similar characteristics between those two landscapes that leads to like a similar emissions or the peak? We don't know yet. Yeah. And yes. And then this one is in Senegal and Niger. I don't know, it's 3-4D graph, but I will explain to it. Here you have the time, of course, in 2023. You have like different crops. And then you have here we normalize the data to be able to fit all of them inside. And here you have the sowing season, the growing season in green, and the harvesting period in yellow. So we try to put all of them inside, and within the graph, you will have in red the land surface temperature, and in blue is the rainfall, and in black you have the methane emissions differences between like cropland versus non-croplands. We just try to see what are the relationship between the three. The first thing we saw is, you see this triangle is the same here, but with a difference in terms of area. And usually you see also that for the peak of methane, it means that temperature reach a certain level, but the water has to reach a certain level. It's not completely aligned, but it means like you have to have a certain level of water first, reaching a level of temperature for methane to start. And when we look at the literature, they say the three parameters that are prominent for methane emissions, they are the availability of substrate, organic matter, the water depth, and also temperature. But among the three, temperature is the highest parameter that is influencing methanogenesis. So meaning that at some point you have to reach a certain level of temperature to start seeing methane going up. And here we also see the same. Water is going down in terms of rainfall. Most of the African agriculture is rain-fed. That's why we look at the rainfall. But for the methane to go up, actually we look at temperature also has to reach a certain level to start seeing the peak again. So we don't have an exact science about this. That's where we're discussing with the national research centers and then trying to figure out, is it something really we can dig deeper and start understanding the reality on the ground, okay? And then here we have the one this is for Niger. So the temperature here is pretty constant at some point here. And for the methane to go up, you see that water has to appear first. It's declining, but it means that here by this time, water is already stagnant on the ground. And then therefore you have the methanes going up again. So what we were trying to show here is that, is there any sort of relationship that we can derive by analyzing the methane emission from tropome, and then by looking at temperature and rainfall, climatic parameters? That's what we were trying to do here. Now, I'm going to stop here for this presentation. These are the results that we have, but I will be very happy if you can scan the QR code. You will have access to the chapter. You have access to the report. There are, I think, 15 chapters there. Next year report will be about emerging technologies, so there will be a lot of AI and stuff like that. Now we are working on measuring the carbon stored in trees in Africa. Why? Because when countries are reporting to the UNFCCC with the national forestry inventories, usually they only consider forests that are labeled as forests, but not trees outside of forest. And in the Sahel, there are some estimates. There are 1.8 billion trees in the Sahel that are not being counted in the NFIs, meaning that either you are underestimating or overestimating your carbon budget, but it will be more underestimating. So now that's what we're trying to do as a next work, and then how to correlate it also with this work. So the data set is already processed for the entire continent. So here we just show some use cases for Senegal, Mali, Niger, Nigeria, and Namibia, and some use case also for Senegal and Niger. So we are trying to build partnership to develop a mixed approach to estimate methane from livestock. It's very challenging. I know a lot of institutions are trying to do the same actually, and try to link it with remote sensing data is very challenging because they move. And how can we make sure we can track them? And it's not that easy. But this is something that we would love to see happen, and we are open for collaboration as well if there are some colleagues that are interested for that. Let me stop here for now and open to questions. Thank you. All right.